We started last time with the rendezvous problem in elliptical orbit, which was the coplanar maneuver. So, at the end of the lecture, we went into discussing about why the non coplanar maneuver is required, and we were discussing about that. So, in that context we made a figure, and in that figure we saw that suppose this is we were discussing that we may be forced to launch the satellite from some certain latitude lambda, because this is our country. Our country is say located here in this place. Okay, so, we cannot go here and launch here in this place. We cannot occupy somebody else's space. So, we are forced to launch here in this place. If we are forced to launch here in this place, so we need to launch along this circumferential direction, and that naturally gives the initial inclination I. And the situation was that we want to put the satellite in the geosynchronous or the geosynchronous or the geostationary orbit. So, for that the I need to be either 0 or the small having a small value. So, if we are doing that, then obviously in our figure we can look that this I need to be reduced. So, for reducing this I, we need to give impulse here in this place. So, this initial velocity is say in this direction, okay, and then the velocity, the impulse must be given in this direction to bring the satellite in this plane. So, this is out of plane things, and then we need to put here in this. So, delta v is given by the line which is shown here. Okay, so, this is your delta v, and this is the original direction and this is the new direction. So, this is the change required. So, therefore, by applying out of orbit impulse, we will be able to change the inclination of the orbit. Okay. So, if you do this, you apply the impulse here in this place, then you will be able to change the inclination. If you apply at some other place, then your capital omega, which is the nodal angle, will also get affected. So, let us start discussing about this. So, we have the non coplanar maneuver requirement. A launch site may restrict the initial inclination of the orbit from which it must be transferred to the desired orbit. Sometimes it may happen that direction of launch can influence the amount of impulse required so at the launch certain orientation may be more desirable from which again we need to do the change. sometimes timing constraint may dictate a window that is not the ideal situation. So, timing constraint may force you to launch along certain direction, and that may not be the desired situation, then you must make the change. So, for this reason we have to change the orientation of the orbit. Suppose we have a vehicle here in this place at B. Okay, so, this is the space vehicle and this is moving in in an orbit whose radius is. So, this is in circular orbit, in circular orbit of radius 3 r, where r is the radius of Earth. So, this distance is basically your 3 r from here to here. Okay, and this x, let us say this is x, this is y and this is z. Another satellite you have, which is a line here in this place, and this is at point A, and the distance from here to here, from this point, and this is r. Okay, if this is the situation and here you have this vehicle, this is the first vehicle, say first vehicle, and here you have the second vehicle. And this is moving along this circular orbit of radius r. And this vehicle, let us say this is moving in an elliptical orbit in the x y plane. So, here this is moving in x y plane in elliptical orbit, and this is elliptical orbit. And for convenience we can assume that this is the perigee position of the vehicle. Okay. So, vehicle 2 is at A and is its perigee position. Now, as this vehicle B is moving in this orbit, so at certain latitude, let us say this angle is lambda equal to 30 degree. So, this is the new position of B, which we are writing as C. So, we have to give impulse to the vehicle 2 in such a way that it goes here and catches up C, catches the vehicle 1 at the position C. So, this becomes our transfer orbit. This is your and the vehicle 2, it is moving in an elliptical orbit. So, vehicle 2 is at A and is its perigee position, and let E equal to 0.4 for vehicle 2. Okay, now you devise your plan how to send vehicle 2 from position A to position C, where the rendezvous has to take place. So, for this rendezvous to take place here in this at C, so this trajectory must be designed. For this designing this trajectory, now you can see that here this radius is r, while the distance from here to here, this is 3 r. Okay. So, obviously, this is not going to be a circular orbit, this is bound to be a elliptical or the hyperbolic orbit. So, what we are going to do, we will assume that let us assume, as earlier we have done. So, in the plane OCP, okay. So, in the plane OCP, which is given by O C and then this trajectory in this P, somewhere the perigee of the transfer orbit lies. So, this we show as P T, which is the perigee position for this. Obviously, this whole thing is coplanar, but here it is not appearing this way. It is not very possible to show this 3-dimensional thing. And obviously, the inclination of this the new elliptical orbit from this old elliptical orbit, this will be give 30 degree, because if we rotate it and bring it into this position. So, we have one orbit here in this plane and we are rotating it by 30 degree like this. So, it will match with the new transfer orbit. So, we have the new transfer orbit, which we can hatch it like this. Okay, so, this is the new transfer orbit, we can hatch it like this. This is constituting one orbit, and P T is the perigee position of the transfer orbit. This is the perigee position of okay, and what is its location. So, location of P from O P. So, this is O and this is P T from O P T. So, we can write here the angle P O P T as, let us say, theta p, or here because this we have named this as A, position A. So, we will write this as theta A. So, this angle from here to here, this becomes theta a. So, now we have described the problem what we need to do. So, formally we can state the problem like this: let a vehicle B is moving in a circular polar orbit of radius 3 r. in the yz plane. Another vehicle at A is moving in an elliptical orbit of eccentricity E equal to 0.4 in x y plane. So, B is located in the equatorial plane. Vehicle 2, we write here vehicle 1 is located in the equatorial plane at B at the epoch, and vehicle 2 is located in elliptic orbit in equatorial plane at A. Okay, so, in fact, the vehicle 2 is moving in the equatorial plane only, and this is an elliptical orbit. So, R B is 3 r and R A is r. Eccentricity is 0.4 of original orbit, and for polar orbit obviously the eccentricity will be 0. It is required to determine the impulsive velocity requirement at A, so that vehicle 2 catches vehicle 1 at C, which is located at a latitude of 30 degree. So, this is the formal statement of the problem. Now, how to proceed? So, we need to go exactly in the same way as we have done earlier. So, all the steps involved are exactly same, nothing different here. So, first of all we will work out in the y z plane the time period of. So, the step 1, calculate TBC, time taken to go from B to C for vehicle 1. So, this is the position B and this is the position C, which is at 30 degree, and this is along y direction and this is along z direction. This distance is given to be 3 r. Okay. So, TBC, this will be given by this whole time period for going in one circular orbit, and that can be proportionally scaled for the 30 degree angle. So, this is 2 pi times 3 r by mu 3 r whole cube by mu under root, and then obviously whatever this angle is. So, let us say that we write this as angle beta. So, we write this as angle beta. So, this will be beta divided by 360 degree, where beta is in degree. So, beta equal to 30 degree. So, this gives you the time of the transfer from B to C in the circular orbit. Now, these values are known to us. So, we have the radius of the earth r is 6378 kilometers, mu is given to be 398,600 kilometer cubic per second square. Okay. Beta is here 30 degree. So, we are just proportionally scaling it. This you could have written in terms of the radian also. If you write in radian, this also you need to express in the radian, but ultimately the ratio will remain same. Okay, this ratio is not going to change. Okay, so, if we now put these values, so TBC will become 2 pi times 3 r to the power 3 by 2 under root mu times 30 degree divided by 360 degree. So, this becomes pi by 6 mu under root times 3 r to the power 3 by 2, and inserting the value of r. So, TBC will get reduced to 3 times 6378, and this will give you approximately 2195. Step 2, assume theta a. So, theta a we have assumed here in this figure. As shown here, this is your theta a from this place to this place, this is the angle from here to here. Okay. So, assume theta a. So, let theta a equal to 5 degree. Next, calculate E t given theta a from above step and known R a and R c. So, this is for the transfer orbit, E t is for transfer orbit, and this angle from here to here. So, the angle POC we will show as POC is nothing but 90 degree, and this we will show as phi. So, OC is located from OP by this angle pi by 2 or 90 degree. So, we need to calculate E t. So, earlier we developed the equation for E t. So, E t we wrote as R c minus R a in a particular elliptic orbit. So, we have now the shown by this green line. So, green line is here in this place. So, this is constituting one transfer orbit, though it is appearing little non-planar because of this black line, but it is a one plane in which the transfer orbit is located. So, the angle from this perigee line or periapse, which is OPT to OC is nothing but theta a plus phi. So, the angle PT OC, this is theta a plus phi. So, we can utilize our old relationship that we developed, or either we can freshly work it out. So, we have R a by R a equal to L by 1 plus E cos theta a, and R c equal to L by 1 plus, and here T we will put here to indicate this is eccentricity of the transfer orbit, E t cos theta a plus phi. And therefore, this implies R c by R a So, we divide R c by R a here, and as usual we have done. So, this will get reduced to E t equal to R c minus R a divided by R a cos theta a minus R c cos theta a plus phi. So, in the third step we can calculate this value. Now, RC and RA these are given to us. So, RC is 3R and RA is R, and this becomes 3R and cos theta A. So, theta A we have assumed to be 5 degree, and RC is again RA is R, sorry, RA is R and R cos 5 degree, and this is 3R cos theta A is now 5 degree and phi is 90 degree. So, R will cancel out in the numerator and denominator. So, this will be 2 divided by cos 5 degree minus 3 cos 95 degree. So, this is the value of E t. So, E t can be computed and it will turn out to be 159025. So, this is the first stage we are working out here. Okay. Once we have done this, so the next step will be, this was step number 3. So, step 4, calculate A. This is the semi major axis of the transfer orbit. Okay, but before calculating A, using the relationship plus minus r by 2 minus r v square by mu, you need to calculate this particular value. You need to calculate this. Okay. So, here E t is given to be, E t is just now we have worked out 1.59025, which is greater than 1. So, therefore, hyperbolic transfer orbit. Now, compute r v square first, and therefore, then you will be able to compute the value of A, and this we need to work it out at the position A. So, r A by 2 minus, and here we can put the subscript A on all the places. So, at A we are calculating the semi major axis of the transfer orbit. So, r A v A square by mu, this we have written as 1 plus 2 E cos theta A plus E square. Just now in the lecture, before, we have derived this equation. Okay, now compute this value. So, r A v A square by mu, this will be 1 plus 2 and E is 1.59025. Sorry, this okay, cos theta is 5 degree and plus 1.59025 square zero to 5 cos 5 degree. So, computing this quantity, so we get the result 2.591635. So, this is your R A V A square by mu. So, therefore, A will be R A by R A V A square by mu minus 2, because E t is greater than 1, and therefore, we have to consider the negative sign in this equation. So, this will get reduced into this form, and inserting all the values here. So, R A equal to nothing but, so this becomes equal to R A equal to R, okay, and R A V A square is 2.591635 divided by mu. This quantity we have copied here, this quantity we are copying here in this place, and this minus 2. Now, this value is given to us 6378 divided by 0.591635, and this will turn out to be 10780.30449 kilometers. So, A the semi major X transfer orbit, this becomes 10780.30449 kilometers. So, here in this, for the non coplanar maneuver, we instead of just doing the writing the equations, we are taking a problem and demonstrating how the whole thing can be worked out. So, because the basic equation we have already developed, so there was no need of repeating the same thing, rather than a problem could have done this. A problem can show this concept in a much better way. So, we are following that. Okay, once we have done for A, so the next step is step 5. Now, given or with known theta A, phi, E t A, compute T A C. So, going back into this equation, now T A C you have to calculate. So, first you have to, let us depict this transfer orbit in the elliptical form here. So, you have this point O and this is the point P t, this is the point C, and somewhere your point P or point A is lying here, which is the perigee position. Perigee, instead of writing here P, we can write here as perigee, and this we have done just for convenience. Equally, this could have been a non perigee position, but it then becomes more complicated to do it as an example in the lecture class. So, this is your theta A, this angle is theta A, and the angle from here to here, this we are writing as phi, which is nothing but 90 degree, and this theta A we assumed it, this theta A we assumed as 5 degree. So, to find out the time T A C, we need to find out the time to go from this place to this place and from this place to this place and subtract it. So, TAC will be equal to TC minus TA, and since the transfer orbit is hyperbolic, therefore, we need to use the equation that we have developed for hyperbola earlier. So, T for hyperbola, T being measured from perigee position of A is the perigee, here you remember A is the perigee position of original orbit, while PT is the perigee position of transfer orbit. Okay. So, we are concerned here with right now with the perigee position of the transfer orbit. Okay. So, this T can be written as A cube by 2 a to the power 3 by 2 divided by mu times E t times E t square minus 1 times sin theta. Let us say this is theta 0 is the position of the satellite in the orbit at which we are calculating the time, or 0 we can drop, just we can write theta here. So, this equation we have written earlier. Okay, so, using this equation, so we can write TAC equal to TC minus TA. So, therefore, TAC will become A to the power 3 by 2 divided by mu under root, and in bracket we will have here E t times E t square minus 1 under root sin theta a plus phi divided by 1 plus E t cos theta a plus phi. Here theta a we have taken as 5 degree assumed, and phi is given to be 90 degree, which is nothing but the position of the, this angle is your phi from P, this is AOC, okay, angle AOC. Here we can change this to sorry, this is PT OP, this is okay, or this we can change it to A, because the P we have changed to notation, the P notation we have written as perigee. So, instead of this we are using this A. Okay, so, AOPT is theta A, this angle, and AOC angle AOC is phi. So, wherever we have written earlier, this needs to be modified little bit. Okay. So, this the earlier we have written as this as the POC. So, we can modify this and write this as AOC equal to 90 degree equal to phi, and again this is POC is equal to theta a plus phi. This is fine. Okay. So, little bit modification here and there, rest are fine. It is only in the little bit in notations. So, here this the rest of the terms we can complete ln E t plus 1 under root plus E t minus 1 under root tan. Now, the total angle is from here to here, from this line to this line, this total angle is theta a plus phi. So, that is entering here in this place. So, here you will have theta a plus phi divided by 2, and this divided by E t plus 1 under root E t minus 1 under root tan theta a plus phi divided by 2. Okay, and this has to be closed in another curly bracket. So, we are closing here in this place, and this minus. So, this quantity is your T c, and same way we have to write here for T a. So, for T a only sin theta a will appear here in this place, E t cos theta a minus ln. Okay, this is not the dividing line. E t plus 1 under root plus E t minus 1 under root times tan theta a divided by 2, and this divided by tan theta a divided by 2. Then this bracket gets closed, and then the large bracket gets closed. So, this is your quantity T a. So, T a c equal to T c minus T a, which we have written here in this place, and you need to insert all the values in this equation. So, in this equation now you can see E t we have already calculated. So, that value turned out to be 1.59025, okay. And then A also is available to us 10780.30449 kilometers. Okay. So, therefore, and theta a is you have assumed to be 5 degree, and phi is given to be 90 degree. Okay. Rest all the quantities are known there inside this equation. This is known, mu already known to us, this is 3986000 kilometer cubic per second square. Okay, it is known, theta a phi is known. Okay, therefore, we can compute this quantity, and if you work it out, so T a c will turn out to be 1939.7267 second. So, this is the value of the T a c. Now, while in step 1 we calculated T b c equal to 2195.0208 second. So, we can see from this place that T a c is not equal to T b c, okay. And therefore, we need to repeat again from step 2, where we assumed the value of theta 2. So, the next step will be, this was our step number 5. Okay. So, the step number 6, if TAC equal to TBC stop, or if TAC and we can say if TAC not equal to TBC, then go to step 2 and again assume a value of theta a. So, if we assume the value of theta a, so obviously we need to iterate. So, again we need to go to the step 2 again going to step 2 and assuming theta a to be 15 degree. So, then you can calculate E t equal to 1.147853 if you assume theta a and follow all the steps, and you will have a equal to 42351.8598 kilometers. This is the semi major axis of the transfer orbit, and TAC will turn out to be 2292.4687 seconds. So, still you can see that this is not equal to TBC, which is equal to 2195, this is 5, this quantity is 5 here, 2195.0208 second. So, this is not equal to, then again go to a step 2. So, we need to iterate once more, because now this is closer to this. Okay, so, time is getting over. So, we will continue in the next lecture, but we have reached quite close to the value which we have taken here. This TAC is coming 2292.4687 seconds, and while the original value is 2195.02 seconds. So, little bit difference is there. So, we will be able to part this difference in the next lecture. So, we will continue in the next lecture. Thank you very much.